All right. Well, welcome everyone to another installment of our great seminar, the Relatorium seminar. And today we have a treat with one of our long-term members of our group. But first, a quick announcement. So we have a special session on JMM, which now has a schedule that has gone live. uh, which has a lot of people that have already given talks on the same seminar before, like Irfan and Priya are going to talk, Edmund, and also talk by Ted. And I see even more people here that may give talks there. So I'll post the link to the session in the chat here so you can have a look. And I think I've already posted it, but so you can have a look and see, and hopefully you can all attend. And for today's talk, so we have Ted from the Nueva school, longtime member, and he has a very interesting title, which is compassion, um, well, for composition or compassion and composition combined into one, which sounds very intriguing. So, Ted, why don't you tell me a little bit about it and give you the floor?
Certainly, yes. I think I might, if I have a knack for anything, it might be titles, but we'll see if the substance follows. But it was so compelling, so I had to latch on to that. Um, yeah, so I want to keep this conversation very light and interactive. I want to model what we stand for, and so please, at any time, feel free to raise your hand. And I think Niels and Priya maybe will moderate. I'll try to keep an eye out as well, and um, I will stop at various points and ask questions, ask people to contribute, because I want to be reacting to things that you say. I have some things that I'll share with you, but mainly I see them as starting points for conversation. So, all right, let me maybe share my screen and get started.
Perfect.
Okay. So here we go. So, and by the way, this is a QR code for this slide deck in case anyone is interested in getting it, because there are links in it that I might not be able to go through. There's more material in it than probably I'll get through. Okay, so maybe I'll say a couple of words first about my story, to where I come from, what brings me to this space. So for me, math has always been kind of very close to my heart. Has been a language with which to explore the world, even as a kid. I distinctly remember. So it was never I mean, it was never something I needed to prove myself in. It was sort of very close to my heart and very natural. And I'm not sure precisely why, but this has been my experience. I was very lucky to grow up in environments that supported me to do that, and to be given opportunities to expose myself to others like me. Um, for example, when I was very young, at the age of the students that I teach now, I was heavily involved in the Math Olympiads. And through that, I'm talking in the 80s, 1980s, so quite a while ago. I got to know and build relationships with a number of people who ended up defining some of the mathematics that we do these days. And so I got to sharpen my very immature thinking at the time in those environments. To give you an idea, I met Terry Tao in when he was 12, and I was 17 in the Warsaw Olympiad. He was the little kid of the Australian team that everybody looked after, while the rest of us were trying to have fun. And or Svetlana Stankova from Berkeley, who I'm still in touch with. We spent several evenings trying to puzzle out cool problems. And at the time, there was no email, so we would send letters to one another with ideas about problems. So this is the sort of the background that brought me into math. And when I a little bit later, I went to MIT. I left Greece. I grew up in Greece. I should have said that. I went to MIT to study math. I was extremely lucky because Irving Siegel, who was an old professor at the time, took me under his wing, even as a freshman. And so I started doing, undergraduate research, which I didn't know what research in math meant. I just had ideas about math. I brought my notebooks with various ideas that I didn't know how to express and explain to anyone. And he took me under his wing. And as an undergrad, I continued to work with Siegel. I learned many things from him, but most importantly, he introduced me to various people, including John Baez, who was then he had just gotten his PhD. And so, of course, John was instrumental over the years. I followed his career very closely, and he was the one who, a couple of decades later, introduced me to category theory. I never thought I would do that. Siegel also introduced me to Paul Erdos. That was, some of you might know who that is, and it resonated with me a lot. I sometimes think of my career in math as, in a very small way, following in Erdos's footsteps. And the most surprising thing about Erdos was that he was even shorter than Siegel, and had a very firm handshake. I remember that. I remember telling him my name, and and later on, Siegel introduced me to Dan Struck, who became my PhD advisor. But before that, he introduced me to Is Singer. And Is Singer was, for a while, the person who was basically teaching differential geometry at MIT. He was sort of the godfather of differential geometry at MIT. And that was my passion as an undergrad. And so I took classes with Singer, and I got to know his grad students. And at the end, just as I was transitioning into grad school, he introduced me to Yuri Manin, who was a visitor of his at the time for a year at MIT. And so let me move to the next slide here. So Manin is an exceptional mathematician, someone I didn't know at all. I was surprised. I didn't even know his name at the time. But he took the time to meet with me. He eventually became the director of the Max Planck Institute of Math. But this was a little before that. It was probably a year or two. I think it was 92, maybe 91 or 92. A year or two after he gave this famous plenary talk at the International Congress of Mathematicians in Berlin, and this mathematics as metaphor, which has influenced me greatly over the years. The reason I'm sharing this is, and maybe you're getting an idea now, that for me, math is all about connections. And so, and the compassion with which so many people, both, more brilliant people of my age that I met, as well as these, many older famous people who had much better things to do than to be with me, showed me. And so over the years, Manin was instrumental in advising me to not give up on my interdisciplinary ways as I was starting graduate school, which was a very rare advice, a rare piece of advice. And I followed it, and it has made a huge difference for my career. It came natural to me to be interdisciplinary because for me, math was not a discipline. Math, as I said, was a language with which to explore the world. And I had interests in many different disciplines, and in how they opened different windows into the world and into the ways of being. So I have this quote here, which I often share. So it's a link. This is a link to the paper. Maybe I can just pull it up. So you can see this is the talk that Manin gave in 1990. But this quote in particular has stayed with me for a very long time, and I keep finding new depths of meaning here. He quotes James Carse, and in speaking about the unspeakability of nature and how that underlies the possibility of language. The way I describe it to people, to my students, many times is that we make deliberate mistakes in speaking about anything, especially math, because clearly the words that we say aren't the things that we mean. Nevertheless, we make sense of them, and that's part of the game. It's very powerful. Also, I take I take to heart the message that he ends this particular quotation here, where he says that we cannot tell what math teaches us, just like a piece of a novel, a piece of literature. But the teaching is sort of recursive in some ways. It teaches us in itself, in rethinking what we're doing. So again, this is meaningful as I'm a teacher. I have been a teacher for many years.
Could I ask a
So
quick question? Just
absolutely,
to
please. Thank you. It's got a
start a
little
bit of
heavy,
a
so I want to lighten
discussion.
the atmosphere now. Yeah.
No, you said, I don't know if I misheard, but at some point you said that metaphor can be used as a tool for connection or to create connection.
Yes.
But
Yeah.
what exactly do you mean by that?
So let me thank you. This is perfect. And it wasn't even planned. It wasn't even a seeded question. I will say, so I'm looking at my notes. I will say at this point, if you read Manin's article, and he eventually compiled a lot of other writings in a book by this title, but in this original article, he talks about two specific metaphors, and he outlines the connections that they bring out to him. One is about Kolmogorov complexity. And this is the idea of trying to make sense of what computational complexity is and what Kolmogorov did in trying to do that. The analogy with randomness, which was very surprising if the first time you think about it. So it's an analogy between computational complexity on one hand and randomness on the other hand. And the other metaphor that Manin brings out is Arrow's impossibility theorem in social choice theory, where the Arrow is talking about choices that people make and how we can combine our choices in groups, and he uses essentially combinatorial and ultimately became understood at this point as geometric argument to do that. So again, metaphor as a bridge between different domains of knowledge. I like to ask people, what are the metaphors that are meaningful to you? If you have metaphors that to you have helped you make sense of mathematics.
I can say, there's a bunch of examples I can think of, but I like the description as certain constructive things as a game, basically. They may use a game in order to prove equivalence between certain, programs. And I guess, it's both technical, but also a metaphor, I think.
Yeah, it's a way of thinking. You're right. I think it has the attributes. This is what I was thinking. Knowing you, Niels, that a game involves players, involves strategies, involves competing goals, occasionally the possibility of collaboration. There's a set of rules. Sometimes the rules can change. So it mirrors mathematics in many ways, mathematical settings like axioms, for example, and the attempt to prove or disprove, the sort of dialogic view of proof, right? That they're opposing perspectives is the person who states the claims and the person who tries to dispute the claims. And then sometimes, we change the rules. We add a new axiom or take away one if we think it's too easy to prove with them. Yeah, that's what I had in
And
mind. And
Edmund wants to say something now.
oh yeah, please, Edmund, go ahead.
I want to give another example of a metaphor that was very useful in me thinking about mathematics. I'm probably going to prove myself to be a mathematician by going very meta on it, but because so this article was also very important to me. And the notion that the metaphor of thinking about mathematics itself as a metaphor was a very useful way to sort of recalibrate what I thought about mathematics, or well, to identify how I thought about mathematics differently from mathematics in science, and sort of be freer in how to think about mathematics in the world, and how we also and our model of mathematics as science, sort of breaking some of the ways that we might want to think about and use mathematics, with game theory being a great example of that. So
Yeah. Yeah, thank you, Edmund. That's right. I mean, it's a very meta thing, right? It's recursive. And I think,
A quick one, Ted, if you don't mind, like a metaphor I use to specialize 13 to 15-year-old probability and game theory. This is city-wide, so smart kids. For the game of hex, you prove that an optimal strategy exists, but imagining the board as the map of US and rivers as being one player's color and kind of mountains the other player's color. So a river flows from Canada to US to Mexico or vice versa.
thanks, Yorgo. Yeah, that's a great example, indeed. But what I wanted to show you guys is this, which I happened to find fairly recently and in a very roundabout way, which goes to reinforce this notion of connections. So this is an article from 2020, I guess just a few years ago, and it's an attempt to formalize metaphor and to use, in fact, categorical language to do so. It's a very interesting, this is a link as well. I don't, there's a link to the article, which I won't open at the moment. But the roundabout way in which I got to this is because I met Hayato Saigo in a completely different context, in a collaboration that I'm doing in the area of sort of categorical probability theory. And he's a philosopher actually working in a bio setting, and so he pointed me to this work, and it's fascinating the connections one can find if you maintain a sort of an open mind towards these bridges, and I'm fascinated by this work. By the way, there's I think the potential to move it forward. It's a start, it seems, of a literature on this field. Let's see in the chat. Yeah. Oh yeah. Yes. So here's another thing that's been instrumental for me. I wasn't aware of this for quite as long, but for several years now, and I bring it up again to my students very often, and it has changed my way of thinking about mathematics. This is something that is quite old, more than 100 years ago. Poincaré, in a fairly well-known article, actually, in the that in English appeared in the Monist in 1910, but was written a little earlier, describes math as an art. This is what resonated with me, Edmund, but as specifically the art of naming different things the same, or giving the same name to different things. At the time, some of you guys, my collaborators, will remember I was fascinated by this, what I called the game of spot the similarity. I even spoke at JMM a year or so ago about that. So this resonated with me, and I brought it as an example. And he goes on to essentially in the article describe how there's obviously an error being made, but it's a very deliberate error when you do that. And the power of math, the language of math, and the process of doing math as bridging disparate domains. I would even venture to say the more disparate the domains, the deeper the meaning of the connection. Do you have any examples of this phenomenon that you are aware of, that you might bring up? I am told as a teacher that this is the most uncomfortable time, to make sure that students have the time, to sit with the silence. But over Zoom, it's a little even less comfortable.
So what kind of example are you looking for? Because
So
I'm
I'll tell you, I
yeah.
have my favorite examples. So one example that, again, several times I've spoken about is the notion of a vector, for example, right? And it's something that resonates with students. And I recently was visiting a linear algebra class where notions of this kind came up. And you go from the concrete of drawing an arrow and saying, so is a vector, is this a vector? And they say, what you say, so what is a vector? And people tell you a definition, it has magnitude and direction, and then you draw an arrow, it has, and then you draw another arrow has the same magnitude and direction, but it's distinctly a different arrow, right? And you say, so is this a different vector? Is it, and you get to the notion of equivalence class. And I know that Edmund and I have recently had a nice conversation about how all of math essentially is about equivalence class. Or a very large part of what it means to, have a mathematical conversation is to, understand the appropriate equivalence classes of things you're talking about, which is exactly this, right? Exactly the ability to name things that are all different instances, but as the property that you want to boil down to. Same can be said about polynomials, and there are many examples. Obviously, with vectors, we can think of, abstract vectors, right? Matrices are vectors as well. For example, later on, I'll give you an even more out there example of that. But yeah.
What about equivalence classes themselves?
Right?
Are they also an
They
example?
can be deformed. Yeah. Yes. I see, Priya. How do you choose the right word? I think you're right, because here, Poincaré implies that, naming is an important act in the doing of mathematics. And I must say too, although I don't have handy the reference for it, this is one half of a reference. The other half that I use, the other half being from the 1930s by an American mathematician whose name escapes me. I do have the reference somewhere, but if anyone happens to by chance know it off the top of their heads, please raise your hand, who says in response to this, and poetry is the art of giving the same name to different things. I mean, different names to the same thing, right? So to disambiguate even further, right? Like different kinds of love, let's say, or different kinds of the color purple or whatever. So names are very important and should be chosen with care. But I want to move on to yet another, this is the trifecta sort of big ideas, and then we'll go into examples. But this is probably, you're familiar with this book. Bill Byers wrote it, I don't remember, maybe 20 years ago at this point. But I have highlighted, taken out a little bit where he's been talking at this point about Andrew Wiles, and Andrew Wiles' description of his thinking, the sort of the idea of where does mathematical discovery come from. It mirrors a little bit Adamar's idea from the late 1800s about mathematical creativity, if you know what I mean, a classic text there. But Wiles talks about the sort of, the metaphor of walking in a dark room and trying to find your way around. And sort of Byers relates that. And Byers explicitly in this point here that he's trying to make is he's juxtaposing, on the one hand, the view of mathematics as the light of reason, he says, where the primary aspect is the logical structure that the practice of mathematics imposes on a situation. Juxtaposes that against this notion that Wiles has brought up in the narrative just before, of the creative light, which emerges from ambiguity, right? And those two seem to be opposing poles, right? On the one hand, you have light of reason, on the other hand, you have light of ambiguity. And what I'm interested in is specifically the end of this quotation, that somehow what he sets out to do in this book that purports to be about how mathematicians think, is to actually show that even though these two appear opposite, they're really two sides of the same thing. There's sort of to create a synthesis, something that can hold both of those seemingly opposing things. And in a way, this is what I'm setting out to do as well in this talk, where I want to demonstrate what I've been calling, I've co-opted this name, the yes and experience in mathematics. The notion that this comes, where I say the yes and experience, some of you may have heard of this before. This is something that you learn in theater school or in improv school, right? And I myself learned it from Alan Alda in his from his podcast and his material. He has videos and talks that he gives about communicating science to lay public and so on. So it's a practice that I have found very useful. I do often see myself as an educator to be essentially an improv artist. A bit, I get up in front of people and have some things to say, and hopefully I want to elicit some positive feelings from them. So you'll see a bit of that going on. This is sort of the guiding principle for the rest of the talk, the yes and experience, how things that don't seem to jive together are juxtaposed, creating the impetus for the person to think bigger, to think what structure might there be that could possibly hold both of those seemingly opposing things together. And I want to shed light on that being a part of mathematics. So let's get to doing some mathematics. Okay. So suppose somebody says there exists a square root of -1. There's a time when you didn't know that was a possible thing, but anyway, let's take it for given. And you say, yes, and it has many logarithms. Infinitely many logarithms. That's a response to it, because you could have said, no, it's not possible. Or you could have said, yes, but no number squares to -1, whatever. No, you say yes, and you double down on it, and you say something more, ridiculous out there, right? Okay. And then somebody says yes, and their differences are multiples of pi. Right? Now, we all know that all of these statements are true, but certainly we didn't know that all the time, and they're not obvious statements. The important thing is I'm demonstrating, what I'm trying to get at is this practice of doubling down and enlarging the space of possibilities. So when you do the yes and in the context of improv, well, what I understand, I'm certainly not an expert on this, but this is what I've been learning, I've been sort of getting into, is the notion that every new statement wants to enlarge the set of possibilities that are entailed in the previous statement. So consider the set of, the feasible set of the previous statement and find ways to build on it. So that, in other words, you want to enable the next person to have more things to say in unexpected ways, to open up possibilities. Don't narrow it down, which is often, often we want to narrow things down. This is and I'm not saying there's no room for that. Of course, that's useful at some point, but I'm encouraging people to consider ways to open things up rather than close them down. Somebody should be looking at the chat. I can't be. So I think there's some comments in the chat. Let me know if
I will do that. Yeah, it's not me who is writing in the chat.
Okay. So. Okay, no worries. That's fine. Okay, so here's another example. There exist infinitely many distinct square roots of the identity. Yes, and their set is at least two-dimensional. Yes, and it includes a copy of C2. Right, so you see how you say even more outrageous things that are even big, in some ways creating more possibilities. And again, now, I mean, these might not be as obviously right as the previous ones, but they are certainly worth thinking a little bit about. And clearly, as mathematicians, you would want to disambiguate them. Perhaps your instinct might be to say, yes, under what conditions? What do you mean by a copy? Is it an isomorphic copy? Is it those types of course, yeah, that is part of mathematics as well. Before I move any further, do you have any similar ideas, any similar examples, and any to build on these or others?
So maybe a question first.
Yes,
so
questions as well.
When you yes, so you yes and then the statement that you're adding is that, so that's not a consequence of what you first said, or is it an extra assumption? Yeah.
It's not meant to be. It's meant to be as an extra assumption, something that isn't obviously refuted. So you're trying to engage with it, right? You're trying to compose statements. Okay, so I'll mention this at this point. So one of our collaborators, who I don't know if she's present, Arpita, probably not present because she's not a mathematician, but she is a collaborator of ours. And she's a sociologist of science. And she has introduced us to this notion, which I was familiar with from before, but had never brought two and two together in the context of mathematics. The Leibniz's notion of compossibility, which sounds amazingly close to composability, is a core categorical notion. But compossibility was building on his notions of monadology and basically looking at what given a universe, given a statement about the universe, this a certain uncertainty set, let's say, or a feasible set from a set of statements. What are other things that are consistent with it? What are other things that can be said that do not refute the previous thing? So this is very similar to that. And there's, I think, a good long philosophical tradition in thinking about building worlds that way. Even going to up to Alain Badiou that Edmund we were talking about yesterday. So this is a long philosophical tradition. But
I can try an example if you want, or
yeah,
because I was thinking, so there is an infinity, and then you can say yes, and there is an infinity that you can't count, basically, and yes, and there is an infinite amount of different infinities, and then you can kind of.
What I want to do, hold on, I want to let's just practice here. I want to start a whiteboard. Can I do that? Is there how can I do that? Maybe I should stop sharing the screen. Maybe I should do it this way. Sorry for okay, here we go. Yeah, I can do
I want to make a quick comment.
Sure, please.
So this process, I mean, it's very intriguing. It's like going very constructive, right? Like even if when things are so ridiculous, you just construct more ridicule and like see how it evolves. And this process is not unique to just mathematics. Like it applies to every field of thought, I think. Is that right? Yeah.
Yeah, it's actually bringing, I think, bringing mathematics into, or rather showing how mathematics interacts with our way of being human, so in our ways of thinking as humans, and our ways of making sense. So I see math, I told you from the beginning, I see math for myself as a language to make sense of the world. So, to explore the world, I said. So it's a sense-making mechanism and when I say math, by the way, this is another important distinction I want to draw. And when so I think it's important to distinguish the product of math from the process of math. And I'm focusing primarily here on the process, not because I don't believe in the product, but because too many people too often think of math just as the product. And my interest is in sort of disabusing people of that notion, that I want to showcase more the process of math, the way of doing math. And so creating new ideas, for example, disambiguating things or creating bridges and connections. So here I just wanted to, I'm sorry if I'm struggling here a little bit, but I wanted to, oops, there we go. What was it that you said, Niels? Can we, Can you tell me? Tell me again.
Yeah, just yeah, it's difficult to phrase, but like there is like infinity. So
There is infinity. Okay.
yes. There can be an infinite amount of things, I guess. Or that's
Yeah, there is an infinite cardinality set. Oops.
yeah.
Yeah. Oops. Well, I can't write here cardinality set. Yes.
Then
There
I
can
guess you can. Yeah,
no,
yeah,
please go.
please go ahead.
Oh, no, please go ahead. I was gonna
Yes,
give
and?
another statement for that.
Yeah,
Yeah. Yes, and?
please.
There can be a bigger infinity compared to that infinity.
Yeah. So maybe can I like maybe say something like not all such sets have equal cardinality,
Mhm.
right?
Mhm.
Something like that. But
Not
essentially
all
what you said,
infinity.
I put a
Yeah. Yanis
not all.
says, Yanis has a comment in the chat
Yeah.
I would like to read. So first he said,
Okay, go ahead. Yes.
a Russell wouldn't include understanding the world type of math into real mathematics. For real of mathematics, for Russell, applied mathematics is not mathematics. And then he also says, not all infinities are born equal.
Are born equal. Yeah, no, that would have been a good way to put it here. And I do the comment about Russell resonates with me a lot because being interdisciplinary as I am, often people try to pigeonhole me, right, and say, so are you an applied mathematician? And I've or what kind of mathematics do you do? And I have changed my response to this over the years. In some sense, though, I just don't believe really in the distinction. And but my mind has changed and is changing, and I think Russell's mind also changed. I mean, for most of his life, obviously, Russell struggled. At least my understanding of his struggle is between the logic on the one hand and pragmatism on the other hand, right? So from a philosophical perspective, the sort of the ontology of logic on one hand and the reality of the real world on the other hand, and how the two don't correspond so well together. But on the other hand, I will say that his theory of types and the whole motivation behind it, in my mind, is an avenue towards category theory, and to the reasons why we come up with the structures that we do. So it's certainly related. So what else? What would be? Let's do one more. What? Yes, and on this.
I think he was hinting at the traps language poses
Yeah.
into us.
Thank you. Yes,
And that's
indeed.
what you wanted, I think, by saying, do not project your parochial understandings or visualizations of what a certain mathematical concept may mean. Do not bring that into mathematics. I think that's what he was trying to preempt, and later the whole the whole Gödel tricks that you cannot formalize something within. If you formalize it, it's going to be either inconsistent or incomplete, but that's an artifact of language, I think, not necessarily of the logical relations. But I think, in any case, that's
you're right, Yanni. And I think some of it was in juxtaposition to Wittgenstein's early views and the language as a game as entirely constructed, devoid of the need for practical connection. So what we would today call, for example, a sort of formal semantics or something of that sort. But I think the other aspect of Russell that I think he struggled with is also the Platonist aspect of, is math some, that he talks about the austere beauty of mathematics as a piece of art that is not made by us, but on the other hand, that we have the undeserved sort of privilege of appreciating in some ways. This is a perspective. I think math is bigger than all of us. All the things that we can possibly say about it, it's bigger than that. So it's a perfect example of the yes and, in that it doubles down on anything that we say and says yes, and I'm more than that. So absolutely. So who am I to take the perspective of math, right? But yeah, but you see the idea, and obviously the power of infinities notion, the you know, including theory types, or also you know, the inaccessible infinities and theory of ultrafilters and so on can be built out of what we just said over here. I just wanted to try out the whiteboard. I'm sorry, this was a very practical consideration on my end. Let me so how am I going to do that? I think I'm going to go back to, just give me a second. View. We're getting better at this. This is definitely work in progress. I want to share my screen again. Continue. Okay, go back to the presentation. Okay, so if you will permit me at this point, oh, actually, you know what? I want to share my screen. I want to share this this little video. But I want to make sure that when I do the share, I optimize for sound. So hopefully, let's see if this works. And I'm not going to do it over the drive. I have it downloaded on my computer, so I will stop sharing. Sorry, this is confusing. It's my bad, but I will share this here. Yeah, here we go. Okay, so this is some students. It's a couple of minutes, not very long, so just bear with me.
If I made this 0, yep, then in that case, the points I have on the circle would be vectors like this. And then I'll just have the 0.
Because it's true.
Yeah,
as my y.
Yeah. Meanwhile, if the origin is,
then my vector would look like this. And then I'll have to add vectors like this. And I don't get the same thing.
you still get a circle, though, right? You still get a circle with the same distance. Yeah.
Wait, is it the same distance?
I think so. Or the same radius?
This is just a linear transformation.
Is it the same?
Adding a.
I know what it is.
If
you want to learn one theorem, I don't quite understand.
I don't. Yeah.
So the results inspector has the same magnitude.
So, right, if we've got if we have a circle, right? Let's just say even our circle is at the origin right here.
Yeah.
And let's just add any point here. Let's not even bother adding the origin. Because we add a point, and if we add, let's say, this point here, it is going to be just translating the circle up here, right?
Oh, that makes sense. That makes sense.
One down, one more. Okay. You good with that, Jason? How all points, all unit circles, no matter where they are they're the same shape, so their location doesn't matter. Okay. Great. And because if we add a point to a shape, it just gives you the original shape. Points are like the identity of our space. They're the zero of our identity. Yay!
I think that's does that have to be the origin point? Because as we just demonstrated here.
That could be any point.
Oh, right, because they move around.
Any point, it's gonna just like translate.
So we have like infinite identity with them.
Infinite. Well,
but
it's
they're all the same.
It's all a point. It's all points are the same. One point is the same shape. There we go.
Well, it has an identity.
It is the identity.
Okay. So let me now go back to my all right. Well, first of all, okay, now that I see you, I see some of you are smiling. I assume you could hear the sound, right? It came through. Okay. So this was from last fall, about a year ago, when I was teaching a course on geometries, and this was a topic, convex geometry was here. So I have some things to show you about that, but just first reactions. What do you guys think? There was certainly some fun being head, which I had fun.
The chat has been very active, and George
I
is
see, but I can't read it. So sorry. Yeah, I'm
And
glad. I'm so glad. Yeah.
the joy of mathematical dialogue and discovery.
Right. And the kid in purple, his name is Caden. Actually, both of the two main kids are now in college. They were seniors last year. And how he has this tendency of jumping up and down and he gets excited. It's fascinating. But
Georgia says AAA mathematicians.
Yeah.
Accepting.
So I wanted to couch. Yeah. Sorry, go ahead. No, Niels.
I am interested what the prompt was. What are the yes ending?
Right. So I mean, yeah, how they got at. So I'm gonna try to couch it in ways that self-contained for us here. But there was a broader conversation. But I think this is the thrust that I'm interested in here. So consider the set of convex shapes in n dimensions. Let's call it Cn, right? Yes. Okay. And in other words, yes and okay. So the point is, this is a set whose points are actually themselves sets, right? And let's endow it with an addition. It's called Minkowski addition. And this is the way you define it, right? This is fairly familiar stuff. The kids already were past this point. If you saw that was written already on the board, they were trying to make sense of that in some ways. Right. And so we say now, questions that arise from that, is A plus A the same thing as 2A? That's not obvious. It requires a proof. That was actually one of the problems they had already done at that point. But, to prove it formally, algebraically. So here we have an instance of multiple representations, right? The algebraic representation, set notation, whatever, and then the geometric representation. And the notion that the idea we're talking about is what's common between them. These two things taken at face value are very different things. One is a set of symbols, the other is a set of shapes, which, are different kinds of symbols, perhaps, whatever, right? None of them are the thing you're talking about. The thing you're talking about is the thing that can share both of those as facets of its existence, right? So then you have to probe it in a formal way, and there are formal ways to do it, like trying to prove that A plus A is in fact 2A, right? But what about that? Is negative A the additive inverse? That's a question I didn't ask them. They came up with that, actually. They had come up with it separately before this in their exploring. They each maintain a portfolio of sort of thoughts that they come up with, open questions, and then possible answers over time. We spent about a month studying convex geometry. So, and it turns out, no, that's not the additive inverse. And you need to come up with a Grothendieck construction to create inverses, kind of like how Grothendieck defined the integers from the natural numbers by pairs. I don't know if you're familiar with that, because it's a pretty canonical sort of categorical construction. And they came to this. So this was one of the original prompts early on when we had started, is in what way can we understand the set of convex shapes as a vector space, right? Which at first felt completely alien to them. And at that point, by the time they were starting to do this already, it was becoming more real and plausible. First, they were pushing back against that notion. Like, how can a shape be a vector, right? And it turns out, actually, this is something that's being done, which I didn't know at the time. Well, I mean, I knew this time. I have been teaching this class for a little while. I didn't know it the first time when I started teaching it. This is fairly new stuff, about maybe 7 years ago, this work, where it's what's called a Riesz space. So it's a sort of the resulting structure is a sort of a lattice-based vector space, but it's pre-order. Unlike on the reals, but it's basically a vector space. I mean, in many ways, it's the properties of the vector space, which is powerful. And how is it powerful? Well, okay, so for example, you can define, this is something that came from the students, okay? So they were being creative about it. We can define what they call second order convexity, all right? In other words, because now you have this vector space structure, you can create linear combinations of those vectors, right? Linear combinations of or what we would call convex combinations of the sets themselves, right? So when is a set of sets, right, convex? And you see why they call it second order convex, because everything in there, even the points, are convex, you know. Question, is there a second order non-convex subset of Cn, right? So even though Cn is made up of all things convex, can you make non-convex subsets of it? Yeah. And how are you to think about it? How can you visualize what that would be like? Is it a transformation, you know, a sort of interpolation between two convex sets that is done in a non-convex way? How, you know, or is it definitionally impossible to do, right? So this is demonstrating, again, the power of names, we said earlier, right? To conjure up thoughts that we never had before. You know, this is obviously abstraction. I mean, Eugenia Chang talks about this very eloquently, better than I, but I just think there's some concrete examples that when I see this in action, being a teacher, I have this privilege of seeing these things happen in action. And so I value them and take them out and hopefully sometimes share them, like now. Here's another direction one can take it, right? Because after all, this was a geometry class, or geometries class, I should say. So yeah, we had Minkowski addition, but what about if we added a metric? And usually in a vector, well, in this space, in the case of convex sets, we often add the Hausdorff metric, which is essentially, and we usually, in fact, at the time they read Ravi Vakil's paper from maybe about 8 or so years ago about doodling, or maybe 10 years ago, about doodling from the Mathematical Monthly. I highly recommend it. I think it's from 2013 or so. Anyway, this is the idea of doodling around a shape, and as you do more, it becomes more and more convex, right? So they wanted to understand some notion of convergence in convex, but of other shapes that are not convex towards the convex shape, its convex hull and so on. So let's say we have the Hausdorff metric, right? Which is just the boundary around it. So distance between two convex shapes, right? Is there an inner product in that? In other words, that metric, is it a norm? Can it be defined as an inner product? I mean, after all, this is on top of being a vector space, right? Can we do geometry on it? Can we find angles, you know, between, if these are vectors, what is the angle between two of them? And it turns out, yes, actually, people have done that. Very recently, just 3 or 4 years ago, they have done that work. And again, I was unaware the first time I brought this up to the students that this was being done. So my point is that some of these questions, and honestly, I don't know the people personally who did this work, so I'm not sure how they were motivated, but I want to point to this exploratory sort of, you know, yes and approach to doing mathematics as a genuine channel towards research in mathematics. So the teaching and the research in mathematics go hand in hand, as they always have. So it's just my little pitch to you know, you can learn. I mean, I thought I knew convex geometry from my Olympiad times. I mean, my main instructor, coach at the time was in geometer, convex geometer. It was you know, a Greek mathematician who made contributions in this field. Sinsifas is his name, in convex geometry, and he kind of you know, I thought I knew. Even in my master's thesis, I did you know, I proved the result in convex geometry. I thought I knew convex geometry, but I had never thought of it this way until I had to teach it. So so yeah. I'm, you know, in the interest of time, I want to stop at this point. I've been talking for long. There's another example, but I'm just going to leave it in there to for people to explore on their own. We'll stop sharing and open the floor. I dumped a bunch of stuff at you. Thoughts, ideas about this or inspired by this?
Very great. There's a lot of discussion, I think, also in the comments. But no,
yeah, I see.
It's a good. That's a very nice idea. So I guess so. I guess in maybe in improvisation, there's moments where you say yes and the moments where you start building, right? Like, is there like a feeling when you want to give a new like get another assumption there, because there's also little risk, of course, that you may get something that doesn't work, but like how do you
Right, that's a good
you have a
point.
good
I
idea
just
of how to
noticed
feed?
I just noticed there was a comment. Sorry to interrupt, Niels. I want to answer your question, but somebody asked for the slides, and so here's the if you could take the URL or the QR code is there.
Let me copy
So
the URL, Ted. I'm putting it in the chat.
yeah. Okay, excellent. Okay. Stop sharing. Okay. So yeah, you're right. I had thought about that
I want
as
it
well.
back. I want it back. I didn't get the full URL yet. Just
Oh gosh, I thought you said oh, okay, never mind. Sorry.
sorry, I was just typing. I'm almost
Right.
done.
Okay. No, that's fine. I don't mind. So yeah, I thought about that, whether so it's a matter of, I think when you observe it happening, or if you reflect on your experience, it feels like modulating between different modalities to me. It feels that way. So obviously not all of I mean, even in improv and in theatrical practice, I mean, not everything is improv, right? And there's technique, there's very, a lot of sort of translating what one person said to something else. Like, for example, I think in musical improvisation, right, in a jazz band, yeah, you have to be able to follow on wherever somebody's riffing, but you might reflect it back at them. The point of improv, the aspect of improv I want to bring up is that not only are you thinking, what am I listening to, and therefore how I can respond to it, but how can I leave it for the next person to say more? Right? So that we're co-creating the largest space we can think of, that can hold the, so we're trying to figure out this big thing that holds all these facets together, right? And we obviously, there's an act of faith to begin with, that we think something exists, and we might find that there isn't, but usually it's taking, in some ways, the flip perspective from, the perhaps more common, more familiar perspective of narrowing down the space of possibilities to figure out whether it's empty. In other words, it's impossible to do it, or maybe there's a unique we converge to a unique answer, and we know that's the thing we were talking about. It's almost like the flip side. So it's more compassionate. Since I talked about this is another, in my mind, it's more compassionate, because you're not trying to rule things out, you're trying to rule things in.
Thank you, Ted. I think maybe Edmund wanted to say something, or
so I really like this approach, but I also think that I'm not sure there's a yes and to it, which is the no but. And so sometimes you actually can, your ideas focus and develop by saying as much what they're not as what they are. And I was sort of thinking through this, and look, what is the compassionate version of that? And I think the dualization of yes to no, but and then reverses to but. And so the trivial example of this would be, we're trying to define a sort of mathematical object in order to prove a particular theorem. And we write down our definition, and then someone comes up and says, there's a trivial counterexample to your conjecture here. That could be, oh, your conjecture is clearly false because, or it could be, well, your definition hasn't captured what you want to say in this theorem yet. And I think in particular, when having conversations with people at different levels of mathematical knowledge, being able to say, no, like what you've just said is wrong, but I see what you're trying to get to, or I think I see I think I see what you're trying to get to. So I'm going to say, no, it's not that, but the other example that comes to mind is, can we try and understand all surfaces in all compact surfaces in 2 dimensions? No, but we can understand them up to from a topological point of view. And so our failure, or the sort of failure of an idea, is the motivation to go to a more subtle idea. And I think having this comes from a philosophical point of view. I think in talking to university administrators, I always love the administrators who say no, and find that that's often far more conductive to a productive and creative relationship. And so I think keeping the value of no in a compassionate way is something that could nicely be added to this idea.
Yeah, I like this dual perspective that you suggest, and I certainly think it's possible to do. What you made me think in how you were saying is it was something that resonates with me, and I didn't mention, and I could have mentioned. So I'm glad you brought it up to me. Is in some sense, okay, let me give it a go trying to describe it. Perhaps the reason I didn't talk about it is because I hadn't thought it through enough, but it resonates enough with me that I have to share it, which is that often in interacting with others, right, in composing, trying to compose, like we say different things, we are talking right now, we are thinking about how what they're saying, relates to something that we have in mind. So we have something in mind, and we're saying, oh, is it agree with it? Does it disagree with it? Is it invalidating? So there could be some emotional overtones with that in terms of its significance, right? And so, for example, just to give an even more specific example, when a less experienced mathematician, say a student, like one of my students or whatever, talks to me or to their professor or whatever, right? The professor often, with the right intention, wants to clarify things for them or disabuse them of misapprehensions or whatever, help them find the way. What I'm suggesting is to do something different, that not because we shouldn't do that, but just as an alternative, as to expand our toolkit, a space of possibilities, to consider the possibility that we don't actually know any better, irrespective of the fact that we have more experience. Consider the possibility that the fact that we have more experience makes us less certain about the world rather than more certain about the world. That the younger you are, the more certain you think you are about what you know. And that therefore, we're approaching this as co-explorers. Maybe there is a thing that so rather than me saying, I'm trying to understand what you have in mind, I'm just accepting that you have perhaps something in mind. You don't even know that you have it, but that there is a thing there that I'm happy to co-explore with you. So, I don't see the world as being made up of certainties. I see the world as intrinsically ambiguous. Because it's of a different type than what I am, essentially. And I'm trying to make sense, since I'm on equal footing with you as trying to make sense. I just have more experience, but typically my experience has taught me that what I used to be certain about is not quite that way. And so, and I feel this is compassionate because it's reducing the burden of authority, if you will, of, students often look to be validated, and so there's, you can make that validation be very contrived, which unfortunately we've all experienced that. Yeah.
Thank you very much, Ted, for this wonderful answer as well. I think this is a good moment to stop the official part of this
it's been an
talk,
hour,
but we'll hang out in a Zoom, I suppose, if people want to discuss things further. I'd also like to announce next talk already, which is by Karen Little, which will be in the November 29th, which will be about exploring the math behind awesome reversible knitting. So that's going to be wonderful as well, I believe. But one final applause for Ted for this wondrous talk.
Thank you. Thank you, guys. Well, I forgot how it feels to not hear the applause. We used to teach for over a year on Zoom. It was common, but thank you.
All right. And we'll stop.
their live stream.
Thanks so much.
Thank you guys for coming. This was awesome. I'm glad.
Thank you so much, Ed.
I should have said at the beginning, I